So transition metals are a section of the periodic table that we kind of ignored in a way. The patterns aren't very good there. And, compared to the other main group elements, the transition metals are very similar to each other. I mean, they're all metals, for one thing. Whereas in the main group, you've got gases and liquids and solids, metals and nonmetals. So common properties of transition metals, yeah?
Yeah, the slide's up there.
The slide shut down. Of course it did. Thank you. Okay, got the projector working again. These are common properties of the transition metals. They have moderate to high densities, good conductors of heat and electricity, high melting points, moderate to extreme hardness. They also have very similar electron configurations. These elements are going to have electrons in the d orbitals. And yet each of these metals is unique, and they do exhibit a wide variety of chemical behavior. I'm just going to go ahead to this one for a minute, because we need to review electron configurations just a little bit. So this is a periodic table that is showing the different blocks of orbitals and sublevels. So the first two columns of the periodic table represent the s block elements. And then there's 6 columns here. Those represent the electrons in the p orbitals, 10 columns in the d block, and 14 columns in the f block. There's a little arrow here. This part of the periodic table belongs in this gap right here. And in fact, the periodic table that we have on the wall in the classroom, we cut it up and put it up that way. Not just because that's how it's supposed to look, but mainly because that's the only way it would fit on the wall above the whiteboard. The periods or rows represent the highest occupied principal energy level. And so you can easily identify the valence electrons. Like if we look at, say, sulfur. Well, sulfur's in period 3. It has valence electrons in the 3rd level. That's the highest occupied level. It has 2 in the 3s, and then we can count across here, 1, 2, 3, 4. It has 4 p electrons, 3p, 4. Shorthand noble gas configuration, you take whatever element you're looking at, you go up 1 row to the end, and you just write that chemical symbol, neon, in brackets, and then you write the electrons that come after that. When we get to the D block, it's a little bit different, because the 4s sublevel fills before the 3d sublevel. So this is not the 4d, this is 3d. So one of the ways I think of that is, it's like it was supposed to be up here, and then, we're coming down the steps, 1, 2, right? That kind of makes sense. But it sank, kind of like the valley floor sinking. So this part sank down. So this is 4s, and then we go to 3d, and then back to 4p. And when we get down here, 6s, and then the next element has 5d1, and then after that, we go over here. And now this one doesn't have a 5d electron, it has 2 4f electrons. So now it's going to fill up the 4f sublevel before it comes back and starts adding in the d orbitals. There are some irregularities in here. We're not going to worry too much about them. Remember learning about this? Right? Any questions right now? So let's go back to this. So as we go across a row of transition elements, we're adding electrons to the n minus 1 d orbitals. So here n is the period number. So the first d orbitals are the 3d, and so they are in the fourth period. In the first two rows, we're going to have ns2 n minus 1 dx. So if n is 4, we've got 4s2 and 3d. And the next one we have 5s and 4d. But then after that, we get down into also having f electrons in there. So this stuff right here is nice, but I think that's just actually very, very confusing. Let's just look at the first row of the transition metals. So they've got 4s electrons. So scandium is in the third column, right, of the periodic table, because the first two, potassium and calcium, are not transition metals. They're main group elements. So here, those are from the first two. Now we're adding electrons into the d orbitals. And so as we go across, we're just adding into the d. Here we have an irregularity because we would expect to keep 2 electrons here and 4 here, but there's energy stabilization in symmetry, basically. So here, by moving one of these electrons over here, both of these levels are half full, and that's more stable than one being full and one being almost half full. We don't need to understand that. It's just what it is. And then it goes back to being predictable. So now we've got 5 electrons here, and then we're adding 6 and 7 and 8, and then we have another weird one. So for copper, we can get better symmetry by having a half-filled s orbital or s sublevel, and then the d sublevel is completely full. It's a very simplistic way of explaining those things. The real reasoning is much, much more complicated. And then for zinc, now we've got the 3d sublevel full. So exceptions. There are a lot of exceptions in the transition metals, and this is because these the s and d orbitals here are very close in energy, and so it's easier to get exceptions. So we've got extra stability of half-filled or completely filled orbitals, and these are the 2 exceptions that I mentioned. Now, when transition metals lose electrons, they're going to lose their valence electrons first. Valence electrons are the highest occupied principal level. And so all of these guys, their valence electrons are in the 4s. They're going to lose those electrons first, even though that's not reverse order of filling. These are a little bit lower in energy than those, but they lose the 4s first. Okay? Questions? Okay, so writing electron configurations for transition metals. Do 2 examples here just to kind of review. So write the ground state electron configuration for osmium, and then for the niobium 2+ ion. So for osmium, what we need to do is we need to find it on the periodic table, which, that's a weird one. So it's number 76. It's in period 6. So we go up to period 5 and all the way to the end to find that noble gas is xenon. So we're going to start this off with xenon in parentheses. And that represents the electron configuration of xenon. And now we're just going to write what comes after. And we can just read these off the periodic table. So after xenon, we come over to the beginning of that S row, row 6. And so we've got 6s, and there's 2 electrons in there. And then we've got lanthanum, which would be the 5d. But then we go into into those, the lanthanide series, and those are the F block. So let's go back to this real quick. So we've got, where'd you go? Osmium, right here. So we've got xenon, and then we go here, 6s2, and this we would add 5d1, but we're going past that, and so we'll take that guy into the f orbitals. We're going to fill up the f orbitals, and then we're going to come back and fill in the d. So the f orbitals are like sunken twice. So the d's are 1 less than the period number, and the f's are 2 less than the period number. So instead of being 6f, these are 4f. So we've got our 6s2, and then we'll go to these guys. So that's 4f14. So that brings us up to this guy. And then we're going to count across, we're going to count this as a D. 1, 2, 3, 4, 5, 6. So there's 6 electrons in the 5D. Whoops, 6 electrons, not the 6D. That make sense? So write ground state electron configuration for Nb2+. Nb is in row 5, number 41. Right here. So we're going to have krypton. And then instead of trying to write the ion, we're going to write the element first and then remove electrons to make the ion. So we're going to have krypton, and then we're in period 5, so this is 5s2, and this is 4d, 1, 2, 3. So krypton, 5s2, 4d3. That's the element. I'll put a 0 up there to emphasize that it doesn't have a charge. How does it become a 2+ ion? Loses 2 electrons. Which 2 electrons does it lose? It loses the 5s electrons. The tendency is to say, well, you just start at the end and work backwards. Well, that works with the main group elements, but it doesn't work with the transition elements. We want to remove the electrons from the highest principal level first. If you heard my Quantum Hotel, a discount resort for electrons analogy of electron configurations in Chem 1A, this 5 represents to the 5th floor of the hotel. So there's some electrons staying there, and there's electrons on the 4th floor, and then everything below that is full. So I imagine it becoming an ion, losing electrons like a tornado coming through. The tornado is going to take off the top levels of the building. It's not going to take out lower ones and leave upper ones, right? So the tornado can't knock out floor 4 without knocking out floor 5. So it's going to clear out 5 first, so we're going to lose those 2 electrons. So Kr 4d3 would be niobium 2+. And you might also see it written 5s0, 4d3. It's just a different way of doing it. Any questions? going to talk about some trends, I guess they're officially called, but they're not much of a trend. We talked about these trends in the main group, and they were more significant there. We talked about atomic size, and we learned that in the main group elements, as you go down in a group, elements get bigger in size, and as you go across a period, they get smaller. So if we look at this for the transition elements, here we've got the first row, red is the second row, and the third row is green. So we see going across, there is a little bit of a decrease in size in the first few, but then the rest of them, there's not really any change, not significantly different. So the number of electrons in the outermost principal energy level is nearly constant. It's going to have those s electrons, nearly constant because chromium and copper are going to drop down to 1. But so we're adding electrons into the d, which is a core energy level, and because of that, adding core electrons, you're also adding protons. It does not change the effective nuclear charge, so it's not going to be pulling them in farther and affecting their size. So going across a row, there's a little bit of a trend in the first 3, but then really not much. So basically they're the same size. Going down a group, what we find is that the second row here in the red, the second row is always larger than the first row, so that's good. That's what we expect. But then there's no increase for the third row. So the third row and the second row are really pretty much on top of each other, and here the one in the second row is actually bigger than the one in the third row. Why is this? This is called the lanthanide contraction, and this is because the F electrons do not shield the nucleus effectively, and so the nuclear charge is a little bit increased and compensates for that extra level of electrons present. So these guys are pretty much the same thing, same size. Any questions? I'm telling you about this. I'm not going to ask you, niobium, osmium, which one's bigger? I'm not going to do that. Ionization energy. We learned that for main group elements, as you go down in a group, the ionization energy becomes lower because the electrons that you're removing are farther from the nucleus, and so it takes less energy to pull them off. And as you're going across a period, the ionization energy becomes larger because the size is getting smaller. Ionization energy and atomic radius are opposite of each other in general. What we see here is as we go across a row, ionization energy increases as expected, even though the size isn't really changing. But going down a group, we see an opposite trend. So the third row has a higher ionization energy than the first 2 rows, which is backwards. This is because the charge of the nucleus is substantially higher, but the atomic size is similar. So those outer electrons then are held more tightly rather than less tightly. Again, I'm not going to ask you to predict ionization charge energies for transition elements. Electronegativity is another trend that we looked at. As we go across a row, we expect an increase, and we generally see that going down a column, down a group. Again, we see an opposite trend. We see an increase from the first to the second to the third in many of these, which is not what is expected. And this is because there's very little size change, but you have an increase in nuclear charge. Gold is the most electronegative of the metals. It has an electronegativity of 2.4, which is actually close to carbon. And so it is possible to have compounds with gold -1 ions, which is not typical for metals. Metals almost always make positive ions. So again, I think of the transition metals as just being kind of squirrely. They're just like, oh, you've got all these trends and rules and stuff. Nah, not for us. And so they're just kind of all over the place. Oxidation states. So for a metal, its oxidation state is equal to its charge. If it's a neutral atom, it has a 0 oxidation state. If it's a +2 ion, it has a 2+ ionization state. And so we learned about these when we learned to name ionic compounds, and we learned that the transition metals, we cannot predict the charges of the ions based on the location of the periodic table because most of them can make more than one kind of ion. The exception that we see in this diagram here is zinc. Well, also scandium. So the rule I taught you in Chem 1A is for metals, if it's in group 1A, 2A, 3A, zinc or silver, it doesn't need a Roman numeral because it only takes one. Zinc is always 2 plus and silver is always 1 plus. Well, scandium is in there too. I left that out of the rule because when was the last time you did a problem with a scandium ion? Probably never, right? So it's like, we're not going to run into it. Let's not clutter our minds up with that little detail. The rest of these guys can form several different oxidation states, several different charges. Manganese is like the superstar here. It can be +2, 3, 4, 5, 6, or even +7. It's huge, big charge. In this diagram here, the most common oxidation states are in the lighter red, and the less common are in the darker red. So like iron, we've run into iron 2 and iron 3. We've never run into 4, 5, or 6. They do exist, but they're much less common. You do not need to know which possible oxidation states these metals have. The +2 oxidation state, you see, is very common. Everything but scandium does that. And that's because you're losing those s electrons. So you lose the s electrons, and you've got a +2 oxidation state. And then we lose one more thing. So copper can do a +1 because it had that irregular electron configuration where it had 1 electron in the s and 10 in the d. And so if it loses 1, it becomes copper 1. Any questions?